When asked whether 3I Atlas could change course or deploy smaller objects that might reach Earth, Avi Loeb's answer was direct. If the object altered its trajectory without significantly increasing its speed, the travel time would be on the order of a few months. That estimate depends on timing and direction, but the physics is straightforward. In fact, Loeb and collaborators worked this out in a peer-reviewed paper published in mid-July. The study explored what velocity change would be required for 3I Atlas to intersect Earth at specific future dates. For every target date, there exists a corresponding velocity shift that would need to be applied earlier along its path. The calculations show a range of possible scenarios, none requiring extreme propulsion, only modest changes sustained over time. That discussion matters because 3I Atlas is not behaving as a passive object. After its closest approach to the Sun, its trajectory should have converged toward a stable outbound path governed almost entirely by gravity. Instead, successive orbital solutions continue to diverge. These deviations are not isolated glitches or measurement artifacts. They persist across independent observations and remain significant even as the data quality improves. Rather than narrowing, the uncertainty in future position expands. Any physical explanation must account for why the motion continues to evolve after the dominant gravitational encounters are complete. Early estimates of the object's size were based largely on brightness. At large distances, 3I Atlas appeared unusually luminous, leading to the conclusion that it might be very large. As closer and higher resolution observations became available, those estimates were revised sharply downward. Current constraints place the nucleus at roughly 1 kilometer in diameter. Under conventional comet physics, an object of this size should show limited activity, especially after perihelion. Instead, 3I Atlas continued to release gas and dust at levels comparable to comets tens of kilometers across. This discrepancy is not marginal. It spans orders of magnitude. Structural integrity deepens the puzzle. A nucleus approximately 1 kilometer wide, shedding mass at the observed rate should weaken rapidly. Progressive erosion, fragmentation, or total breakup would normally follow. None of that was observed. The object remained intact and coherent throughout its most active phase. This implies either internal strength far beyond what is assumed for loosely bound icy bodies, or a configuration in which mass loss does not translate into destabilizing stress. Existing comet models do not naturally produce this combination of small size, extreme activity, and mechanical stability. Orbital dynamics impose additional constraints. The trajectory deviations cannot be explained by planetary gravity alone. They require persistent non-gravitational acceleration, most plausibly from asymmetric outgassing. While such forces are common in comets, they are usually smooth and slowly varying. In this case, the inferred thrust changes in both magnitude and direction. As a result, orbital solutions fail to converge. Predictive paths expand rather than settle, implying that the outgassing is neither isotropic nor steady. Images from NASA's Lucy spacecraft, taken when it was hundreds of millions of miles away, show a compact coma and a faint tail. As observations accumulated, attention shifted from where 3I Atlas was going to what it was producing. The dust became the central clue, not because of its quantity, but because of its uniformity. Instead of a broad distribution of grain sizes, the particles clustered tightly around a characteristic scale of roughly 10 microns. That number emerged repeatedly, independent of method. Smaller particles should have been swept away almost immediately by sunlight. Larger ones should have been too heavy to lift. Yet these grains occupied a narrow physical window that allowed them to linger near the nucleus and scatter light efficiently. Modeling the dust cloud revealed another precise result. Its optical depth sat close to 1, the boundary between transparency and opacity. At that threshold, the dust blocks a direct view of the nucleus while remaining luminous. Telescopes see structure, motion, and light, but not the solid body itself. This is not typical comet behavior. In most cases, dust production fluctuates, optical depth varies, and the nucleus periodically becomes visible. In 3I Atlas, the dust environment appears locked into a narrow, persistent state that keeps the core hidden. Geometry compounds the effect. Alongside the diffuse cloud, observers detected a narrow structure extending toward the sun. At first, it resembled an optical anti-tail, but projection models failed. Physical jet simulations predicted the structure, and subsequent observations confirmed it. For a jet to remain sunward, its particles must be heavy enough to resist radiation pressure. Again, the physics points back to the same 10-micron grains. Light curves reinforce the picture. The brightness variations are rhythmic and persistent, not random. Simple tumbling cannot explain both the light modulation and the timing of trajectory changes. Pulsed outgassing links them. Bursts of brightness correspond to subtle but measurable changes in thrust. The scale of mass loss is difficult to ignore. In the month following perihelion, 3I Atlas shed on the order of 10 million kilograms of dust. For an object roughly 1 kilometer across, that represents significant erosion. Sustained over long periods, it would quickly exhaust the surface. Yet the object appears to retain volatiles. If it spent millions of years in interstellar space, cosmic radiation should have depleted near-surface ices long ago. Either the activity began very recently, or something preserved those materials far better than expected. Chemistry offers partial explanations and new questions. Carbon dioxide dominates the outgassing, not water. CO2 sublimates at lower temperatures, explaining activity far from the sun. Over interstellar timescales, however, CO2 should also be depleted near the surface. Its abundance implies deep reservoirs newly accessed or an unusually well-preserved exterior. Neither scenario is common in small bodies. Jupiter adds another layer. The object passed near the planet's Hill radius, the boundary where gravitational influence shifts. Instead of settling afterward, additional deviations appeared, consistent with ongoing non-gravitational forces during and after the encounter. Geometry, timing, and structure began to align in ways without clear physical necessity. Spectroscopy revealed unusual metal ratios, including elevated nickel. Polarization measurements showed properties not seen in ordinary comet dust. Near perihelion, the object brightened rapidly and became bluer, contrary to typical behavior. Radio observations detected no artificial signals. For some, this supports a natural origin. For others, it simply constrains active transmission during the observation window. Silence alone explains neither the motion nor the dust environment. The difficulty is not that natural explanations are impossible. Many individual features can be explained by invoking rare compositions or extreme conditions. The challenge is that no single natural model accounts for all of them simultaneously. Each added assumption weakens the overall framework. As 3I Atlas recedes, opportunities for new data diminish. What remains is a consistent record of measurements showing an object operating at the edge of known behavior. Its size, activity, dust properties, chemistry, and trajectory do not align cleanly with established comet patterns. Whether it represents an extreme natural outlier or something fundamentally different remains unresolved. What is certain is that its passage has exposed significant gaps in our understanding of what moves between the stars.